We're going to learn about rates of reaction in this chapter. It is chapter 22 in our book. And we have really just been learning about whether reactions proceed or not up to this point. This chapter is going to be talking about rates of reaction, or how quickly a reaction occurs. This is called chemical kinetics. It's an area of chemistry that really just deals with timing reactions. In a chemical reaction, the reaction rate is going to be the rate at where reactants disappear, and guess what? Products appear. It's the change in concentration of the reactants and the products over time. And the way that we write that is we write it with the triangle symbol over the change in time. Okay, so this would really look like a change in concentration over time. And time is T1 to indicate the beginning and T2 to indicate the ending. So you subtract T2 from T1 and you will always end up with a positive reaction rate. The only way that we can determine a reaction rate experimentally, okay, because reaction rates have to change during reaction time, and a lot of times that reaction rate can be so small that they have to do several experiments in order to figure out the average reaction rate. Some of them are so fast that we would miss it, so we have to take an average of them. In order to understand the rate of a reaction, we need to understand a couple of things. We need to understand how the reaction is taking place from the products to the reactants. We call that the reaction mechanism. So we need to know the steps. Okay, we need to know how the bonds are broken, which bonds form first, and we need to know if there's any intermediate products that form before the final product. So in order to determine a reaction mechanism, we need to first of all understand it, and we need to practice. For example, here's an example of a reaction mechanism. Ozone, which is O3, it decomposes into oxygen. So the way that you would write the reaction mechanism is we start with O3, and that's first going to produce an oxygen plus two atoms of oxygen. So we have O plus O2. The reaction is balanced. However, what you'll notice is this oxygen here becomes a reactant in the second part of that reaction mechanism. So the oxygen that is formed here gets used up in the second part, and it reacts again with the ozone. So in the end, what you end up is getting 2 molecules of O2. Okay, so that oxygen in step 1 becomes a reactant in step 2. The individual steps are called elementary steps, and they have to add up to the overall process. So what that means is that the substances that are produced in step 1 that are consumed in the next step, like this oxygen, for example, it's produced in step 1 and consumed in step 2, that is called an intermediate. Okay, so that intermediate is what is produced in the first step and consumed in the second step. Now, reaction rates have to be determined experimentally because every elementary step, every step in a reaction has its own rate, has its own speed at what can happen. One step can go really fast and another step can go really slow. So if we think about laundry, I have a load of laundry washing right now, and there are several steps that take place in order for me to take out a clean pile of clothes from the washing machine. Okay? The washer fills with water, it gets agitated, the clothes get spun, the water fills with rinse water, the clothes get agitated again, and then the clothes go down for their final spin. All of these steps add up to the final product of getting your clothes washed, but they don't take the same amount of time. Many times the washer filling up with water is the part that takes the longest. In chemistry, the slowest elementary step is called the rate determining step. The rate of washing depends on all of the steps, but especially that's that rate determining step. Okay, so it's kind of like if you're on a relay team, and each member of the relay team can run at a certain speed, can run at a certain rate, and your concern should be on the slowest person on your relay team, because they become your rate determining step. If they can run faster, then the entire team can run faster. It should also make sense that the rate of the reaction is going to be influenced by how much reactant you have. That's called the rate law. So the rate law is an equation that we can use to determine the reaction rate for any given concentration of reactants. Okay, so if there's a change in concentration of one reactant, is that going to affect the reaction rate? That's what we have to figure out. And we measure the reaction rate of one particular reactant using a variety of concentrations. Okay, and then we do the same thing for every single reactant. So here is what a generic reaction rate formula looks like. You have A and B. Okay, A and B are the substances in the reaction. They're the concentration of those reactants. Okay, so they're going to be in moles per liter. That's taking into account only two reactants. So if we had a third reactant, we would call that C. And the exponents are the powers of the concentration of reactants. You have to be given those in a problem. Okay, K again stands for a constant. It is a rate constant. It's a fixed value. Okay, so we don't ever have to solve what K is, but this is a very generic rate of a reaction formula. And there are two important tips I want you to remember when we're solving these. The exponents don't come from the coefficients just like they have in the past. Because most of the reaction rates happen in a series of steps, those numbers will be given because they have to be determined experimentally. Tip number 2, not all of the reactants appear in the rate law. If changing the concentration of a reactant doesn't affect how fast that reaction is going to go, then we don't include it in the rate law equation. The exponents in the rate law are called reaction orders. That's the overall reaction order is going to be the sum of all of those exponents. So if you have a reactant that has a higher reaction order, it's going to have a greater effect on the reaction rate. Okay, so in this case, if we look at this reaction rate, notice the K is a constant, it really is insignificant in this case, then this has a 1 exponent and this has a 1 exponent. In order to figure out the reaction rate, we have to add the exponents together because that tells us the reaction order. So in this formula, the reaction rate would be 2 because I have a 1 on the NH4 and a 1 on the NO2. Since NH4 is raised to the first power, the rate doubles when I double the concentration of NH4. If I also double the concentration of NO2 because it is to the first power, then I also double that concentration. Okay, so those exponents in a rate law actually show how the rate is affected by the concentration of each reactant. Here's an example. If I have A plus B, that's going to produce C. The rate law, again, is the concentration of each of the reactants, and it gives me that B is to the second power. That would be given to you. So the reaction order, remember, is the sum of the two exponents. In this case, it would be 3 because this A has a reaction order of 1. Let's practice solving these 3 problems. Rank the following in order of increasing reaction rate. So what I have to do is I have to figure out the exponent for all of these. So if I count all my A's, I have 1, 2, 3, 4, 5 A's, 1, 2, 3, 4, 5 B's. So this reaction rate is going to be A to the 5th and B to the 5th. So let's do this next one. I have 1, 2, 3 A's, and I've got 1, 2, 3, 4, 5, 6, 7 B's. So the reaction order is going to look like this. A to the 3rd, B to the 7th. The last one, if I count, I see that I have 7 A's and 3 B's. It's going to look like this. A to the 7th, B to the 3rd. So the rate law tells us that the concentration of B has a greater influence on the rate than A because it has a higher reaction order. So the mixture with the highest concentration of B should react the fastest. Okay, so if we look at all of these three, now I realize are out of order. This is reaction 1, this is reaction 2, and this is reaction 3. If I look at the reaction rate formula for each of these, it told me that the reaction rate for B is higher. So I put it as a second power. Okay, this is how I end up getting these answers. The answer would be number 3. Okay, this one would react the fastest, then number 1, and then number 2. When I do the math, k times 63, that one is going to react the fastest, because notice it's got a 63. Okay, then the first one is next, 125, and then 147. And I'm going to stop here.